The work is called Black Box Characterization of the Effects of Laser Pulses on Mega 328P. So yeah, Mega 328P, that's a kind of a microcontroller. And the motivation for doing this is, so often people assume that there's a certain fault model and then they base their attacks on that, or they do an actual attack on a device, but then they say, okay, it's probably an instruction skip fault, but nobody actually looks at what, well, the number of works that look what actually happened is very rare. So our aim was to find a fault model for this microcontroller. There's a little bit of a disclaimer to this because the Mega is kind of an old microcontroller. It is built in, I think, 350 nanometer technology or something like that. It's rather old, but it's still widely used. So it's a very common microcontroller because it's the one that's used on the Arduino Uno platform. So that's also the platform we use because it's very convenient. And yeah, Mega comes in a bit package, which makes it very easy to decapsulate for us. But our setup, our laser injection setup works for backside fold injection. So that means that we have to decapsulate the device and expose the substrate of it. Therefore, we have to tweak the board a little bit. So in the back of it, we added a little connector. We bent over the pins of the chip. We delayer the package with a hobbyist mill. So with a 500 euro mill, you can open the package perfectly. And then if you take a picture of it with a near-infrared camera, you see something like this. So the dimensions of the chip are 3 by 3 millimeters. And this picture is taken when the substrate was thinned a little because the size of the actual substrate of the chip is 500 micrometers. So if you look at that with a near-infrared camera, you're not gonna see anything. So we thin the substrate, and then if you take a picture of it, you can clearly distinguish the 3 main regions, which contain the flash memory, a RAM memory, and then the logic. And then in the rest of the chip, you have some analog circuitry that do, for instance, clock regulation. So this is the platform that we're targeting. And for the picture, we tinned the chip, but for the actual fault attacks, or for the actual characterization, the chip was untinned. So we just used the mill, removed the metal paddle at the back, and that was it. So this is what our fault injection setup looked like. We have the target board here, which is the Arduino Uno. And it talks to a PC. So the computer sends a command to the target in the first step, and the target starts executing some code. The target itself also provides a triggering for the laser box. So this allows us to have very precise trigger, which helps with the characterization. If you would do a real attack on a target like this, you probably wouldn't have access to the pins or be able to put your own code on there. So then you would need a side channel to trigger on. But so for our case, we just use an internal trigger. So once the target sends a trigger, one signal generator enables the laser fault injection. We use signal generators because they give you good control of the pulse duration, so the pulse length, the delay between the trigger and the pulse, and the amplitude of the laser pulse, so the power that the laser gives to the target. And so once this thing triggers the laser injects a fault on the target, hopefully injects a fault on the target, sends the data back to the PC, and after the data is sent back to the PC, a second signal generator resets the target. So it cuts the power to the target, and then the Arduino resets. So the laser that we use is a laser with a 1064 nanometer wavelength. So these are designed or used to backside fault injection. So you inject your laser pulse through the substrate on the transistor layer. The laser beam itself is produced by a diode laser and is focused by a 50 times objective. And we have a special beam splitter inside of our optical system. So the laser can propagate through the splitter, but then all the light that's reflected gets reflected to a camera system. So this also allows us to make images and gives us an idea of what we're actually shooting at. And so the entire optical system is mounted on a stepper table that can move in the X, Y, and Z direction, and which has a precision of 0.1 micrometers. Okay. So on the device itself, the code that runs them looks more or less like this. So you have one assembly instruction that enables the trigger, then you have a couple of knobs which isolate the target instruction from all the rest, and then once the target instruction happens, then there are a couple more knobs. So the Mega has a two-stage pipeline, so it has a fetch and execution stage, and for the initial characterization, we more or less targeted cycles 3 until 5 just to find the sensitive regions. And then in the end, we narrowed down our profiling to both the fetch and the execution stages. So before we do the laser fault injection, we put the register file to a known state. We inject the fault, and then after the fault injection, we read out the entire register file again, and then we determine, or then we try to figure out what actually happened to it. So if we target in cycle 3 to 5 and we make a scan of the complete chip, we get a fault net that looks like this. So in this case, we just executed our target code. The laser is triggered, we put a broad laser pulse, and every time something went wrong, we color in that position on the chip. So something went wrong, by this we understand that the register file looks different than what we expect. So then we unfold the register file. So if we do this for the entire chip, in this case we used a pretty big step size, so I think we used a 20 micrometer step size. And there are two main regions. So in the green region we have exploitable faults. By exploitable we mean the device doesn't completely crash. So it sends back a result. It's something we can work with. In the red boxes, the device stops with responding. So there, the device completely crashes, and the only thing that we can do to recover from this state is power cycle the device. So in the rest of the presentation, I'll only focus on the green regions, because the red ones are good for denial of service, but for nothing else. Yes. So if we have a closer look at the green regions, then we stepped over these regions again, and then we cluster different regions based on whether or not they produce the same fault. So here we classify the segments, so for instance segment 11 at the bottom, if we shoot there with the laser you will always get an identical fault. So we can, for the instruction, multiply our registers 23 with registers 27. We get something that looks like this, and we have 11 different clusters, each producing a different fault. So once we had this sensitive region, we ran it again to fault only the fetch or only the execution stage. And for this instruction, we noticed that only the fetching stage is sensitive. So if you introduce a fault in the execution stage, nothing happens. So, and if we then have a closer look at what actually happens. So, the original instruction is we multiply R27 with R23, and then if we fault in a location that corresponds to the first segment, so here at the top, then instead of multiplying R23 with R27, we found that you actually multiply R23 with R26. So we found this by loading different values into the register file, executing it again, and then narrowing down which instruction it could possibly be. So in the end, we figured out that for this particular instruction, depending on the segment where you hit, these are the instructions that result. So the opcode of this multiply instruction looks like this, and the opcode that the opcode of the instruction that's executed if you fault the first segment looks like this. So here we notice that there's only one bit difference. So the last bit, the least significant bit of the multiply instruction seems to be reset to 0. So if we move down in our chip, so this is the, let's say, the top segment. If we move down a little to the second position, then we see that an instruction is executed which corresponds to this opcode. And this opcode, here the two last bits seem to be reset. So by repeating this experiment, you can see that there is a pattern that indicates that there are bit resets in the opcode during the fetching stage, depending on the position where you shoot at, you will get a bit on a different location will be reset. So this can be explained if we look at the general structure of flash memory. So in flash memory, in the AVR, we have 16-bit words. So the entire memory has 16 different sections which all contain 1 bit of every word. These sections are controlled by some controller logic which drive the word line and the bit line blocks, or which control these two things. And then a particular cell of every array is read out and sent over the flash bus. So also, if you look at the picture itself, here you can distinguish nicely 16 separate regions apparently. So these correspond to every one of these, to a single cell array. One of these blocks corresponds to one of these cell arrays. So from this we can assume that during the fetching, if we inject a laser fault on the chip, that we fault a readout of one of these memory cells, and this fault leads to a bit reset, or a bit stuck at 0. So in order to confirm this, we looked at the execution stage of the load program memory instruction. So what this does is it fetches some data that's stored in program memory. So in this case, it loads something from memory location Z and stores it in register 9. So at address 100 and 101, we loaded the values FF and FF, so all ones. So address 100 corresponds to the top 8 bits, or no, to the 8 least significant bits of a single 16-bit word in flash memory, and the address 101 corresponds to the 8 most significant bits of that 16-bit word. So if we now again scan the chip, then we get a picture that looks like this. So if we address the top, if we address the 8 least significant bits, we see that we only fault the top segment, and if we address the 8 most significant bits, you see that we only get faults in the bottom segment. So this confirms that when we read out data from flash memory, that somehow, that we can reset bits that are read out. So there's a second sensitive region, which you can find in the bottom left corner. This consists out of a couple of concentric circles. Each of these concentric circles leads to a particular instruction, but these concentric circles don't have a regular pattern, so they're more difficult to classify what exactly is happening. So, and then the influence of the laser parameters on this fault injection. So if you use the laser energy is equal to the pulse duration multiplied by the total laser power that you put in. So if you use a low laser power, then you will see that your sensitive region reduces and there will be less overlap between the regions. So in the second picture you can see here we double the power. So there are more, the darker the color here, the more bits are faulted, so there's more overlap between the different regions. And so a bigger area is faulted. So how can we use this fault model? So the fault model is stuck at 0 faults for data read out from flash memory. These faults aren't permanent, so if we power cycle the device, the flash memory itself will not be altered. And one of the things we can do is we can introduce faults in the program flow. So you can, for instance, if you have a cycle counter that counts the number of rounds of your AES implementation, then instead of break if not equal, you can flip 1 bit, make it break if equal, and then jump out of your AES after 1 round instead of 10. Or we can introduce faults, this kind of jump, in the data flow. So if you load SBox values that are stored in flash memory, you can fault them and then perform a classical DFA. So in conclusion, we're able to fault data and instructions that are loaded from flash memory. The faults that we introduce are deterministic. And so by knowing the exact fault model of what's happening, you can make very specific fault attacks and very powerful fault attacks. Any questions? Yes?
Why did you choose this device?
Because it's very convenient to use. So it has DIP packages, which is relatively... DIP packages are packages where you have little pins that come out of it. So, and these are very easy to decapsulate with cheap equipment. And also you don't have to make a new PCB for them. So we picked this device out of convenience. Yes?
Do you know why the faults are not permanent? Because they're faulting flash, right?
Yeah, you're faulting the readout of flash.
Okay.
So we don't actually know how the flash memory is made, but probably you're resetting a bus line that's transmit the data that's coming from flash. But the actual flash cells itself, you don't hold it. You don't use it.
But then why? I mean, like from the figures, it looks like spatially it's pretty spread out, right? So I would expect if you're really faulting a bus line, that would be much more localized.
Yeah, me too. Apparently so.
If you're following all lines, so
Yeah, you know.
the energy can just flow towards where you are.
Can you go back to the picture of the reflection? Right, because I mean, this is also something that we puzzled a lot. Right? We have these 16 rows that correspond to the 16 bits of the words. It doesn't matter, you can choose into the LSB of any word, yeah? But you always get the same behavior. What do they have in common? Well, they all must be what connected to these lines. For me, for us, the conclusion was always that we need some drivers here.
Yeah. Yeah, probably some line drivers. Or, yeah, here you have these word line drivers. It might be that we hit one of those things, but it's impossible to tell without actually knowing what the layout is of the flash. To see what's happening.
But probably not one of them, because they must be sitting along the way, so that it doesn't matter where you shoot somehow. Because that's actually one of my comments. That when you have this maps, you should add how many micrometers are this the map size. When you say, oh, we use a large step size, and how many steps do you make on that picture? 2 or 10 or 50? Or, so it must. But it's not that there will be little mirrors on the chip, and so it doesn't matter where you shoot, the light always hits the same transistor, right?
No, it's always the same
transistors, but the effect is somehow the same.
What exactly is happening in there?
But without knowing anything about the design, it's already, we went already quite far, huh?
Yeah, for sure.
To figure out this thing.
That's good. I mean, it's quite targeted, right? What you always want. Like that's like if you think about a fault attack, the most interesting scenario is where you can actually use some value that you wanted to have, right?
Yeah, with this thing you can do very powerful stuff if you want to.
Do that almost. We can make zeros. We cannot make ones.
Yeah.
Happy.
Any more questions?